So, the birthday problem. You probably spent 5 or 10 minutes talking about some ideas about how to attack this problem, or you sat there on your computer and did nothing. Well, either way, this is a good question. So, what is the probability that at least 2 students out of a class of 9 will have the same birthday? First of all, everyone raise your hand if you have a birthday in May. Oh, good for you. You guys are very special. Let's define A as being the event that all birthdays, that no two are the same, at least 2 are the same. At least 2 have the same birthday, right? Because that's what we're looking for. The probability that at least 2 have the same birthday. So the event A is at least 2 people have the same birthday. And just for argument's sake, let's say A prime is, well, if at least 2 have the same, then the complement of that would be no one has the same birthday. Okay? So let's remember this. Probability of event A is equal to 1 minus the probability of A prime. Now, why am I reminding you of the whole complement idea? Well, if you want to attack it from a brute force method where you're looking at least 2 people have the same, well, then you need to consider the probability that 2 people have the same birthday. Then you have to look at the probability that 3 people have the same birthday, 4 people have the same birthday, 5 people have the same birthday, and so on and so forth. And that can get actually really lengthy in terms of calculation. So let's think about it from the flip side, and actually let's try and calculate the probability that no one has the same birthday. And here's how we can think of it. We have 9 people. The first person, okay, or in other words, 1 person. Okay, so how many ways can 1 person have a birthday that no one else has? Well, if it's just 1 person, they're the only person in the room. So they have a 365 out of 365 chance of no shared birthday. Okay? Now that's if we're just talking about a class of 1 person. They have a 100% chance that no one else shares their birthday because they're the only one in the room. Now, the second person, so now we have a class of 2 people. Well, the second person, because let's say the first person is born on May 1st, okay, the first person is born on May 1st, that means that the second person, if they are to have not the same birthday, they have 364 out of 365 chance of not a shared birthday. In other words, a really high percentage, right? And that should make sense. It's very likely that 2 people don't share the same birthday. That's why people get all excited when they have the same birthday as somebody else, because it's so unusual. Now, the third person, now we have a class of 3 people. You can't share May 1st, can't share May 2nd, so 363 out of 365 chance. And if we go all the way down, the 9th person has a 350 what? Let's make sure here. 350, because we know that like sometimes we count strangely. So 365, 64, 63, 4th person 62, 5th person 61, 6th person 60, 7th person 59, 8th person 58, 9th person 357 out of 365 chances of no shared birthday. Okay? So the probability of event A is going to equal 1 minus the probability of no shared birthday. Okay? However, well, what's the probability of no shared birthday? Well, the probability of no shared birthday is the probability that one person doesn't share a birthday times the probability that the second, third, fourth, and all the way up to the ninth person does not share the same birthday. 363 out of 365. So all these probabilities multiplied together, all the way up to 357 out of 365. Those are some big numbers. So let's maybe simplify this a little bit. Well, I know that 365 times 364 times 363, 362, 361, 360, 359, 358, and 357, that's a familiar thing to me. And if I remember correctly, this is why algebra is so handy with stuff like this. I remember that as being 365 permute 9. There aren't that many ways to have 9 objects, or in other words, if we expanded it all out and factorialized it and everything would cancel and we'd be left with all those top numbers multiplied together. So recognizing that allows me to rewrite it in terms of a permutation. Now the denominator, well, there's 365, but there's 9 of them being multiplied together. So it's a power of 9. Now, just to make the point, this is not a general formula, right? So don't just make the generalization that, oh, I memorized this formula and I just switched the 9 for however many people. It might be true for this kind of a question where it says at least 2 students sharing a birthday, but that's not a universal truth thing where you can just use that formula. So beware formulas. So let's do this in our calculator. 365. Oops, I have to reboot my program. 365 permute 9 is that, right? 1.04 times 10 to the power 23. So enormous number. Luckily, I get to divide that by 365 to the power 9, and I end up with something very small, 0.905. Which is equals 1 minus 0.905, which simplifies down to 1 minus 0.905. Well, let's go all the way a little bit more. 0.0946. 0.0946, or a 9.5% chance that at least 2 share a birthday. A very slim chance that 2 people out of 9 would share a birthday, and that should kind of make sense. Really, it should be a small number, right? It's not very likely. Now, some of you might actually look at that and say, wow, that's a lot higher than I thought. Out of 9 people, the likelihood of 2 people sharing a birthday, I would think that would be an extremely tiny number. Well, it's almost 10%, which is pretty big. Anyway, that's how you do the birthday problem. It's a tricky one. But the idea is to show you that once you get to this kind of stuff, sometimes it's easier to look at the complement. Okay? So rather than at least, usually these kinds of words are buzzwords, like at least 2 students, meaning you have to account for multiple cases, or something like at most 4. Well, you have to account for multiple cases. So pay attention to the language and decide for yourself, once again, whether or not it's easier to just do the complement part rather than doing it every single case individually and adding them up. Well, there you go, the birthday problem. Goodbye.